Real-life collisions happen in more than just one dimension. In the earlier videos, everything that we did, we may have described it as all happening in the x direction. Stuff is happening in the sideways direction. There was a force in the x direction. All of the velocities were in the x direction. Here's a force just backwards in the x direction. And we get a really interesting thing that whatever the change in the momentum of one of the objects is in the x direction, the other object has exactly the opposite change in momentum in the x direction. But in real life, collisions happen in 3D. So in this case, I have an object B coming in from the upper left and an object A coming in from the lower left. I don't know what their masses are, but in general they can be different. Collision process happens. It starts at some earlier time and finishes at some later time. It has some degrees of elasticity. It could be inelastic or elastic. It could be super elastic, as described in the earlier videos. It doesn't really matter, or actually, it's not that it actually just doesn't matter. So I've got some outgoing motions of the two objects. This is, I guess, a collision where the two objects don't change. So a piece of A doesn't get carried away by a piece of B. I mean, you know what I mean? Or it doesn't change into 3 outgoing particles or 1 outgoing particle. It just happens to be that it's somewhat elastic seeming. But anyways, the collision process happens, takes a certain amount of time. And here goes the outgoing B object, and here goes the outgoing A object. They have new velocities. The velocity incoming for B and the velocity outgoing for B are different. The velocity incoming and outgoing for A also different. So it looks like in terms of the drawing here that there is a change in the momentum of object B. It's equal to the final momentum of B minus the initial momentum of B. And there is also a change in the momentum of object A. This is the momentum of A final minus the momentum of A initial. All right, so we know, let's say that this collision process happens and only forces, that is, we can speak to the net force, only forces are what happens between A and B. Nothing external happens, right? So there is no gravity, no friction, no nothing. There's nothing else going on. There's not a third object, C, that secretly came in and took part in the collision. So we are assuming that the only forces that happen during this collision process are the exchange forces between A and B. And those forces, the force on B by A, it's a vector function of time, and it obeys Newton's third law. So here is Newton's third law. The momentum, this is given to B by A. The momentum changes because of an impulse given by A to B, right? This due to a force on B by A. And then over here, I kind of made the mistake of making too much motion over it there. So let me put it over here. This is the impulse given to A by B, because B also pushes over on A. So I've got these two statements here, and these two separate statements for a change in momentum are actually connected by Newton's third law, which causes them to be related statements. And the related statements are that delta P sub A equals the opposite of delta P sub B in vectors in 3D, or if you lived in a weird alternate reality, 4D or 5D or 2D, 1D as well. Yeah, so this is because these two impulses are actually opposite. But what I think is cool, and it's probably already occurred to you, the force profile. So I'm just going to make one up. But the interesting thing is there's a force profile in X, Y, and Z. So the force profile, say this is the force on B by A in the X direction as a function of time. So let's look at this. So if the X direction is this way, let's say the Y direction is this way, and the Z direction is out of the page up towards you. Let's look at this. So it kind of looks like B and A are coming in like this maybe, and they have a collision, and A goes away this way and B goes away this way. It could be that B heads that way and A heads this way, and they came in like this or something, so they go in like this and then bounce and come out like that. I don't know. All kinds of stuff can be happening. So let's say that in the X direction there's not much to speak of. There is TS and TF, and let's say that it's kind of small, not much. But you can see that there's a lot of change in the Y direction. B comes in kind of negative in the Y and leaves kind of positive in the Y. That's kind of a bounce in the Y. So let's use a large force between the same two moments in time. So here's the T start and the T finish for F on B by A, but in the Y direction. And let's make it kind of big, right? So that's the time. And then in the Z, F on B by A in the Z direction. In time, still start and finish are the same, likely. And in the Z direction, let's do this. Let's say that in the Z direction, actually, the B object got pushed on by A. It got pushed on backwards. So B came out of the page on the way in and is now heading into the page on the way out of the collision. So it goes without saying, but by Newton's third law, in the X direction, T start and T final are the same moments in time, and you just get the same force profile, just upside down. Likewise, in this case, this is the force on A by B in the Y direction, T start, T final. It's big, just like that. And in the Z direction, the force on A by B is the other way around, because if it's negative on the reaction side, it'll be positive on the action side, right? And this will give rise to an impulse that's opposite. So the total vector impulse given to A by B is related to the impulse given to B by A as a vector, but anti-parallel, backwards, or opposite.